Good morning. Happy Tuesday. So here we are talking about the High School Algebra 1 course. A quick introduction. My name is David Dye. I am currently in my third year of teaching and my second year at Algebra High School. I currently teach algebraic connections and discrete math, but I have experience teaching Algebra 1 from last semester. Our focus for today is the first critical standard. Critical Standard 1, where we're talking about quadratic functions and expressions, but I want to focus our attention to what you see in the bolded section for the critical standard. So today we're going to focus our attention on being able to factor quadratic expressions and solve quadratic equations using a factoring technique. So my goal is for you students to be able to look for patterns across numbers in order to develop a factor finding strategy. So that's going to be the goal today. And to accomplish this, my agenda is that we're going to revisit some prior knowledge. So I'm going to look to activate some things that you're familiar with, going back to some concepts that you looked at earlier this semester in Algebra 1. We're going to start looking at patterns as we try and continue to make sense of some of the things that we've looked at. Use those patterns then to develop a strategy for how we look at quadratic expressions and then factor them. And then apply that strategy, and then we will close out by summarizing the day's lesson and then taking a look ahead at what we have for next week. So what I want you to do is to take a look at these four equations and think about what value each variable needs to be in order to make these equations true. So I'm going to give you about 10-15 seconds just to kind of look through these four equations and think about what values will make each of these equations true. Okay, so as we take a look at the first equation, we've got 6 plus 2a is equal to 0. So I'm looking for a value of a that when substituted in is going to give us an expression equivalent to 0. That value of a, therefore, must be equal to -3. Now with b, we're not looking at only a sum. We're looking at just a singular product. So 7 times what quantity is going to be equal to 0? And here, b must take on the value of 0. So any quantity times 0, that product, is going to give us a 0 as our solution. In the third equation, the value for c, if I'm looking at this particular expression on the left-hand side, this entire quantity must be equal to 0. And so for that to be true, c must be equal to 5. 5 minus 5 gives us 0, and then 7 times 0 is equal to 0, similar to that second equation that we see. And in the last part, g times h is equal to 0. Either g is equal to 0 or h is equal to 0. And these are just some ideas that I want you thinking about as we continue to make sense of why the need for factoring quadratics in the first place. So taking a look at these four equations coming up. X minus 3 is equal to 0. And in order for this equation to be true, the value of x must also be equal to 3. 3 minus 3 gives us 0. In the second equation, something a little different but kind of similar to what we saw on the previous slide. I've got the value x times the quantity 2x minus 10. So how can I find values to make this true? Well, similar to that g times h scenario, in this particular case, one quantity, x, must be equal to 0, or the second quantity, 2x minus 10, must be equal to 0. So here I've got two solutions where x is equal to 0 or the value of x is equal to 5. And again, this is a theme that's going to continue to come up as we look for patterns across the work that we do today. In the third expression, we've got on the left-hand side x minus 3 times the quantity x minus 10, and that expression is equal to 0. So when we're looking at these two together, again, that product of one quantity times the second quantity must be equal to 0. Here we've got a scenario where x minus 3 is equal to 0, or x minus 10 is equal to 0. So if I'm looking at these two situations, x here is either the value of 3 or x is the value of 10. Now I'm hoping that all of this again is just a review of things that you've seen before. But if I show you this fourth equation, I want you to take 10 seconds and kind of think about what strategy you're going to use in order to solve this particular equation. So here we're looking at 1x squared plus 8x plus 15 is equal to 0. How do we find values of x that make this equal to 0? Now, up until this point, we haven't really developed a strategy that allows us to solve a quadratic equation that looks like this. So what I want to do now is to kind of take a step back, revisit some concepts that you've seen in elementary and middle school, and hopefully use those same ideas in order to help us figure out a way in which we can develop a strategy that allows us to solve this fourth equation. So what I want to revisit and look at are some area models. In elementary school, you looked at looking for products, multiplying numbers. And here we can see if I've got side lengths of 3 and 3, so a square, the area there is going to be 9. And when I multiply these two together, I can represent that. 3 times 3 is equal to 3 squared. Same thing if I had a square with side lengths of 7, I can represent that area as 7 squared being equal to 49. Or if the unknown side lengths are both represented by the variable x, again, their product can be represented by x squared. And again, this is an idea that we're going to use in order to build a foundation for how we're going to develop this strategy. What if we're not looking at a square and we're looking at a rectangle? So here on the left-hand side, we've got a rectangle whose side lengths are 3 and 12. So the area of this rectangle is 36. If it was 2 and 16, the area then would be 32. But again, if I don't know a side length value, I can just find that product, 5 times x, representing these 5 groups of x length rectangles in order to represent that inner area. Okay, so again, taking another step back, in elementary school, you also looked at the multiplication of 2-digit values. So think about the product of 12 times 13. How would you go about finding this product? And again, we're going to rely on this area model. So if I've got on the top this value of 12 and on the left-hand side the value of 13, I can decompose both of these numbers into smaller values that are equivalent, 10 plus 2 and then 10 plus 3. And then from there, we can then look for areas of smaller parts within the larger rectangle. 10 times 10 gives us an area of 100. 10 times 2 gives us an area of 20. 3 times 10 and then 3 times 2. And when I add all of that together, I end up with this area that is 156. Okay, so that's just the product of two-digit numbers. But how can I use this technique and strategy along with the area model that allows us to make sense of that quadratic that we could not solve? So when I replace these values, instead now of having integer numbers, we're looking at variables. On the top, I've got a side length of 1x plus 2. And then on the left-hand side, a side length of 1x plus 3. So using a similar strategy, like we did with 10 plus 2 and 10 plus 3, decomposing them, so 1x plus 2 and 1x plus 3, I'm going to look for the smaller areas within this larger rectangle. So the product of 1x times 1x is 1x squared. The product of 1x and 2 gives us 2x, and we can see those 2x rectangles within the larger rectangle. 3 times 1x is 3x, and 3 times 2 gives us 6. And again, like that previous problem where we're multiplying 12 times 13 for an area of 156, we would add all of these parts together, the 1x squared, the 2x, the 3x, and the 6. And that'll give us this area here of 1x squared plus 5x plus 6. So let's key in on what we see. Notice up top, I've got these expressions, 1x squared, or I'm sorry, 1x plus 2 times 1x plus 3. And then when I multiply them together, I end up with this expression, 1x squared plus 5x plus 6. So some terminology that I want to throw at you is that this bottom expression, we're going to say this is the standard form. Of a quadratic. Whereas the top part, the 1x squared plus 1x plus 3, is the factored form. And some just general notation, the standard form typically is going to look something like ax squared plus bx plus c, whereas your factored form looks something like x plus p times the quantity x plus q. But these two are related to each other. And thinking back to that area model, we're going to look to see how we can use this relationship between this factored form and this standard form to help us figure out the factors of that original quadratic that we had a question about in order to solve for what values are going to make that quadratic equation from earlier equal to 0. So taking a look at a couple more area models. Here we've got a side length of 1x plus 4 times 1x plus 6. What I want you to focus your attention on in this particular slide is the location of the products, the areas within the larger rectangle, and how it's going to relate to this standard form of an equation that I'm going to show you in just a second. So we decompose our two expressions. We find the following areas: 1x squared, 4x, 6x, and then 6 times 4 gives us a product of 24. And that sum, I don't know if you can see this equation down here, but we've got 1x squared plus 10x plus 24. So I want you thinking about this equation, this total, and how does it come about from these parts? Where are the numbers coming from? How are they related? And then here, we've got a side length of 1x plus 5, 1x plus 2, and again, I'm looking for their products, so 1x squared, 5x, 2x, and 10. And again, we've got this equation, and I want you paying attention to where you see these values and where you see these values. What kind of connections can we make? And so the things that I want you focusing your attention towards is that if I look here, this 1x squared and that 1x squared, think about the location on each of these rectangles. See how they're constantly in that upper left-hand corner. Think about where this 10 is and where that 24 is. These values without an x, these constants, are always in your bottom right-hand corner. And then think about that middle term in our equation, the 7x and the 10x. Where is that coming from? And that's when we combine these like terms right here, this 2x plus the 5x gives us 7x. And the 10x is from 6 plus 4x. So how can we use this structure and these patterns to ultimately help us? I want to take a look at another area model. And we're going to finalize one more relationship before we start developing the strategy. So if I take a look at this larger area model, our top side is equal to 3x plus 4. On the left-hand side is equal to 2x plus 1. So again, as we're looking to decompose these, I've got 1x, 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 and that totals 3x. On the side here, I've got 1x and 1x. That total is 2x, plus 4, plus 1. And when I look for these products, and I combine these terms, I've got 6 total x squared areas, a total of 8 x's here, 3 x's there, and then that 4 at the very bottom. And our total area is represented by 6x squared plus 11x plus 4. The last relationship I want you thinking about in this case is how are these numbers, the 6 and the 4 and the 8 and the 3, related to each other? And what we see is that 6 times 4 is equal to 8 times 3. This 24 is equal to 24. And that holds true in this particular area model, as well as if we go back one slide, these two area models. Again, if I multiply 1 times 24, I get 24. And that's equal to 6 times 4, which is 24. Additionally, if I do 1 times 10 and get 10, it's equal to 2 times 5. Okay, and that's a relationship that we are really going to focus our attention towards. So we've noticed in these examples the location of x squared in our constant term. We've noticed where the sum of these two is equal to that middle term. And we've also noticed that the product along these diagonals, 6 times 4 is equal to 8 times 3. So how can we use that to our advantage? Let's come back to that original problem that we could not solve. So in this particular case, we're looking at 1x squared plus 8x plus 15. So I'm going to sketch out this area model. And how can I use those patterns that we noticed to complete this area model? Well, 1x squared is going to go into that upper left-hand corner. We know that to be true for our other area models. In the bottom right, we know that constant term 15 is going to be there. But what we know too is that these two on our upper right and bottom left corners must add to give us this middle term. We saw that relationship. But we also saw that these values, their product, is also equal to the product of 1 times 15. So let's think about what that means. 1 times 15 is equal to 15. Then I'm also looking for two numbers here in these spaces that are going to be equal to 15 when I multiply them together, but also add to give us that middle term of 8. So if I'm listing out the factors of 15, I have 1 times 15, and I have 3 times 5. Well, if I add 1 plus 15, that's equal to 16. 3 plus 5 is equal to 8, and that right there is what we're interested in. So these two squares must then be 3x and 5x. But now we're still looking for what these side lengths need to be. And so the way we're going to figure out what these sides are is if I look for a common factor. Here, the common factor with 1x squared and 5x is going to be 1x. The common factor between 3x and 15 is a positive 3. The common factor going across here is a 1x. And then the common factor going across in that bottom row is a positive 5. So now we're left with this expression, 1x plus 3, and then this expression, 1x plus 5, that is equivalent to that top one. And now we've got two factors that we can use to find what is equal to 0. I'll set both of these equal to 0. And so the values of x, therefore, are going to be negative 3 or negative 5. And notice how we were able to take advantage of that area model that we were using previously when multiplying two-digit numbers, the area model that we were using previously in order to make sense of the rectangles as it relates to multiplying these side lengths, and how we were able to take this structure and work our way backwards in order to find this particular solution strategy. Let's take a look at one more quick example. So in this situation, we're looking at 6x squared minus 11x plus 3 is equal to 0. Now, some of you might be thinking, well, we haven't looked at a situation where this middle term is negative. But does this strategy and does this structure still work? Well, let's find out. If I'm looking at the area model still, again, what we know to be true is that this upper left-hand corner is going to be that x squared term. In the bottom right-hand corner is going to be that constant with no x values. And again, we know that this relationship, the product between these two numbers and these two numbers, must be equal. So what are the factors of the product between 6 and 3? So 6 times 3 gives us 18. And so the factors here are 1 and 18, 2 and 9, 3 and 6. But notice that we're looking for a sum that's going to give us this negative 11. Well, we see that 2 and 9 here, if I add them together, give us 11. So negative 2 plus negative 9 will give us negative 11. And that is going to be our key here. Negative 2x, negative 9x. And now, again, we're going to look for the greatest common factor along each of these columns and rows. So the greatest common factor between 6x squared and 9x squared, negative 9x, is 3x. The greatest common factor between negative 2x and positive 3 is a positive 1. Going across on each row, the greatest common factor with 6x squared and negative 2x is going to be 2x. And the greatest common factor here between our negative 9x and positive 3 is going to be negative 3. Oh, excuse me. This should be a negative 1. And so when we look at this, negative 3 times negative 1 gives us a positive 3, and everything else still works out. So now we've got these two expressions, 2x minus 3 is equal to 0. 3x minus 1 is equal to 0, and we can solve each of those quantities so that we can figure out what these values of x need to be so that we have it equal to 0. So as we look to wrap up, let's think about this strategy and kind of summarize the steps that we've looked at. If we're looking at a quadratic equation in standard form, like I've noted before, we're going to place the values of ax squared, so where that x squared term is in the top left, that c value in the bottom right corners respectively. Once we have that, we're going to list all of the factors between the product of a and c. Once we've got those factors listed, we're looking for the pair whose sum is going to be equal to the middle term, that value of b that we're interested in. And then we're going to place those remaining values into the upper right and bottom left corners. And once we've got it listed, now we're looking for the greatest common factor along each of the columns and then along each of the rows. And that's going to make up our side lengths. And once we have our side lengths on this rectangle, we've got two quantities that we can set equal to 0 that allows us to then find the values of x that are going to make this true. I want to leave you with this particular problem to think about. How are we going to make sense of 12x squared minus 11x minus 5 is equal to 0? How does that fill into our area model? And how are you going to go about finding the side lengths in order to make this particular equation true? So for those of you at home watching, I want you to copy down this particular problem and think about how you're going to solve this using the area model structure and that pattern that we've developed across this lesson. And so I want to conclude with a couple summaries. So the zero product property, this idea that if I've got a product between two quantities equal to 0, that one of them, at least one, must be equal to 0 itself. And that when we're given a quadratic equation and we're looking for the factors to solve that equation, we can use this area model that provides a good structure for organizing the given information that we have in order to find the factors of our quadratic equation. As we look ahead to next week, so some things that I want you thinking about, questions that are going to prime your brains for finishing out the rest of our standard. Why is it important that we looked at equations today, specifically quadratic equations, that are set equal to 0? Why does that matter? Second, can we solve quadratic equations in standard form that are not equal to 0? What happens if this is equal to 5? What if it's equal to 10? And then lastly, what are the different strategies for solving quadratic equations? Are we only limited to these area models, or are there other strategies that we can use in order to find what these solutions are? That's all I have today. I will see you all next week.